Hello, I'm happy to present our work Painless Stochastic Gradient, Interpolation, Line Search and Convergence Rates that will appear at NeurIPS 2019. In this paper, we present a simple line search mechanism that can improve the convergence rate and empirical performance of stochastic gradient descent. Stochastic gradient descent is the most common optimization method for training machine learning models. These models, the objective function is minimizing a function f of w, which can be a sum of component functions fi. Here each fi corresponds to the training loss on an example I. The HGD update can be given as follows. Here wk plus 1 and wk are the SGD updates. Eta k is the step size or the learning rate at iteration k, and nabla fik is the stochastic gradient evaluated on a mini batch of examples at iteration k. SGD is simple to implement and use and has good generalization properties, especially when training large deep neural networks. However, it suffers from two problems: slow convergence and the need to carefully tune the step size. For example, in this figure, we show the SGD updates with three different choices of the learning rate. The blue line corresponds to SGD with a large constant step size. Because the step size is large, the iterates bounce around the solution and do not converge to it. The red line shows SGD with a small learning rate, and it requires a large number of iterations to reach in the neighborhood of the optimum. The green line shows a tuned SGD. However, the step size needs to decrease as the iterations progress in order to converge to the solution. This results in the slower convergence of SGD. These factors can make the implementation and use of SGD painful. In this paper, we propose to use two ingredients to make SGD painless: interpolation and stochastic line search. Interpolation is a property satisfied by large overparameterized models, including typical neural networks and expressive kernel mappings. Formally, it implies that at a point w star, the minimizer of the function f, where the full gradient is 0, each of the stochastic gradients, nabla fi, is also 0 at that point. This implies that the model is expressive enough to fit all the training data or interpolate it. Previous work has shown that the interpolation property can be used to prove fast convergence rates matching that of deterministic gradient descent for constant step size HGD. We combine this interpolation property with a stochastic line search scheme that enables us to search for the best step size instead of manually tuning it. Combining these two ingredients can result in strong theoretical results and good empirical performance. But what exactly is stochastic line search? Stochastic line search is simply SGD equipped with a line search mechanism. In each iteration k, we compute the stochastic gradients for a given training mini batch. In step 2, we search for the step size eta k that satisfies the following stochastic Armio condition. This condition is a stochastic equivalent of the deterministic condition used in optimization. Essentially, the condition says that the function fik evaluated at a point after the SGD update needs to be sufficiently smaller compared to the function value at the current point. Note that checking the Armio condition involves only the stochastic gradient and the function evaluations on the mini batch of examples. Once we have the step size eta k, we can use this to update the parameters as before. In the paper, we prove that SLS is theoretically sound. In particular, interpolation enables SLS to match the full batch convergence rates for both smooth convex and strongly convex functions. Under additional assumptions, we also prove fast convergence rates for non-convex functions. Moreover, we propose a Lipschitz line search for the stochastic extra gradient method and show its fast convergence for a subset of non-convex functions. The same line search can also be used for a class of saddle point problems. Empirically, we show that SLS optimizes faster and better. We compare against a large set of optimizers and show its superior performance. In this figure, we show the performance of SLS on ResNet 34 on the CFAR 100 dataset and compare it against the best tuned constant step size SGD and Adam. From these figures, we see that SLS can result in lower loss and better generalization performance. In the paper, we considered other models and datasets as well. Besides this, we have results on deep matrix factorization using linear neural networks, kernel mappings, and min-max games. You can try SLS in your project by installing our optimizer. Both the GitHub code and the paper are publicly available. To know more, please come to our poster on Tuesday, December the 10th at 5:30 p.m. Thank you.